All right, next up is question 5. It says compute the integral of the function f of x, y, z, which is 4 minus x squared minus y squared over the sphere of radius 2 centered at the origin. All right, so here's our sphere, radius 2 centered at the origin. Here's the rectangular equation. And here we'll just set a equal to 2 in the parameterization from the table. And so here is our parameterization. Here are the bounds for u and v, and we're taking the whole sphere here. So just as in the table, u varies from 0 to pi and v varies from 0 to 2 pi. All right, so now let's go ahead and compute. Well, first off, for the magnitude of the cross product vector, right? This, as we derived, was a squared times sine u, and since a is 2 here, we're going to get a 4 sine u. And then we have our differential area element dA there. So this expression is our differential surface area element, ds. And then here I'm just going to write this as the function f evaluated along the sphere. So it just makes it a little less cumbersome to write out. Now, one way I could go about finding this expression is just to plug in this expression for x and this expression for y, and then just simplify. And it's not terribly hard. It's just going to be some Pythagorean identities involving sines and cosines. So certainly, by all means, go ahead and do that if you like. But I do encourage you to look for ways to maybe simplify that a bit. And here we can definitely simplify it a lot because the equation of the sphere is x squared plus y squared plus z squared is 4. And so I notice that 4 minus x squared minus y squared on the sphere is just simply z squared. So instead of plugging in the I and the j components for x and y respectively here in the f, instead what I'm going to do is plug in the k component for z in z squared. I just get 4 cos squared u. Okay, it's a little bit simpler. So now we can go ahead and set up our surface integral. So we're going to integrate f evaluated along the sphere. So that's just 4 cos squared u. And then we have our ds surface area element. And we found that that was 4 sine u dA. And we're integrating over this rectangle r in the uv plane where u varies from 0 to pi and v varies from 0 to 2 pi. And that's a pretty straightforward integral. You could use a substitution if you like. You get minus cos cubed of u divided by 3, evaluated from 0 to pi. Notice this is independent of v, so that v integral is just going to contribute a factor of 2 pi there. And so when all is said and done, you get 64 pi over 3. All right, great. That's going to do it. Thanks.